Okay, so let's start the last talk of the series. So this time, Professor Birkar going to talk about male model in dimension 3.
Okay, thank you. So this is the final lecture in this series. Like I said, I'm planning to talk a bit about minimal models. But in fact, most of what I will say would be for any characteristic. That's simply because I would not get to the most interesting part of this thing, because it would be very technical, and then just to talk about fluid would require these 3 lectures. But then anyway, still I will give you some of the really interesting ideas. So the main reference for at least in the characteristic P case, actually characteristic theorem is mostly Caucher. And then for the characteristic P, this is Heiken. So in fact many of the key ideas just come from Caucher work. It's almost identical. But there are some differences which has to do with extending sections. In characteristic 0 you use vanishing, in characteristic P you use forbiddance. Okay, so let me anyway tell you about this story. As usual, K is algebraically closed. So you can take characteristic to be positive, but in fact, as I said, many of the things I will talk about come from characteristic 0. Okay, let me remind you.
I'm sorry. Do you have to worry about small characteristics like a 2 or 3?
Yeah, I will mention this. Actually, for the moment, let's take any time. Just remove this. Because I come to characteristic here all the time. So, okay, let me remind you of certain things. Recall running the minimal model program. So I have mentioned it a few times during the lecture, but there are certain starting points that I never actually talked about. Suppose that we start with xp, let's say this projective pair, because then you can choose your singularities to be Keel, canonical, or some freeness kind of singularities, but for the moment it doesn't matter, just take a projective pair. So remember what I used to do was to take an ample divisor. We choose an ample divisor, let's say A, and then we take lambda to be the smallest. Infimum of all the t such that k is not b plus t and is net. So you're already familiar with all this stuff. If lambda is equal to 0, we already have a minimal model. There's an interesting case where lambda is positive. Lambda is positive. Then we like to show that the divisor given by lambda is semi-ample. So we have seen examples of this situation, like for 3-fold over finite field, or for surfaces. I already actually proved this kind of statement. So we like to show this is the case, and if we can show this semi-ampleness, we get a contraction, a morphing, let's say, f from x to z. So this is going to be non-trivial because it will contract at least one term. Now, there are essentially three very different kinds of contractions. And this is where I never really explicitly mentioned. So we have three quite different. One is called divisorial. And that's when this morphism contracts some divisor, but it is still birational. So, in reality, we like to take this kind of F to be the so-called extremal, but I don't go into this which of technical bits. If you choose this to be extremal, then there will be a better behavior. Like, for example, you could just contract one prime divisor. Anyway, you don't need to worry too much about that. And then there is the case of fleeing. And this is the most problematic case. Here F is again birational. But it does not contract any device. So for example, let's say dimension of x is 3, and F just contracts one curve. In other words, there is no divisor, there is no surface. They contract maybe just one single curve, but these kind of contractions are called fleeting. And in fact, they cause the most headache because, as I will explain in a minute, they don't let you continue the program so easily. And then finally, we have fiber type. So fiber type simply means that dimension of x is strictly bigger than dimension of z. In other words, you have a really genuine fibration. Your x will be decomposed to fibers. So if the final case happens in fiber type, then in fact the program is more or less finished. That's when we get the so-called Mori fiber space case. So if F is fiber type, or in this case, we have a Mori fiber. This is the kind of negative vibration that I discussed maybe in more detail in the colloquium. So for example, if you start with a surface, this could be just like a rule, like a P1 bundle, something similar to that. So these divisorial and fiber type, they are okay because in this case essentially you are done. In the divisorial case, you can just continue with Z. So one obvious example of divisorial contraction is just like a blow down. So the inverse of a blow up. So for example, if you have a smooth variety and if it's a smooth variety, you can blow it up. And blowing down means that the inverse of that operation. So that's one typical example of divisorial contraction. But now what to do with the flip? Well, the problem in the flipping case So in this case, the singularities of Z will be just too bad. So for example, the canonical divisor is not anymore what we call Q-cutting. In other words, you cannot define intersection numbers. So of course, if you have a Caucher divisor on Z, you can still define intersection numbers. But for instance, if just for a minute assume that b is equal to 0, then you on Z you have kz. This is not Q-Caucher. This locally is not defined by one equation. Even if you take any multiple, it's not Caucher. So if you have a divisor, and if all the multiples are not Cartier, you cannot define, you cannot intersect it with a curve. Because to define intersection numbers, you need this Cartier condition. So that's a major problem, and then in this case, the idea is to do the following. Is to find a diagram of this form. So we already have x to z. We like to construct something on the opposite side. X plus, and this is the birational. So the f plus in some sense is similar in the sense that this is also birational and it does not contract and it divides. Let me call this phi, and then what we require also is that kx plus b plus, so this is just the, by definition, this is just the push down of kx plus b. We like this to be positive. For example, you can say ample. So here what happens is that we have k plus p. Here we have kx plus b plus. In this direction, you have intersection numbers that are all negative by definition. So this divisor intersects any curve in this, what is morphism contracted by f negatively. But here, if you have any curve contracted over Z, it will intersect it positive. So in other words, you switch negative to positive. And in topology, there is something similar to this they call surgery. But of course, you can try to do also surgery here, but if you are not experienced enough, probably you end up killing variety. You really need to be very experienced. Okay, so this is what we call a flip. So this whole diagram, this whole setting is called a flip. So this kind of thing in fact exists. They are not just imaginary. So you know, in politics, people usually talk about something just to scare people. But it may not really exist, or it might be just a little problem. But it might be much bigger just to scare people. So this is not imaginary. It really exists, and I will give you one example in a few minutes. Okay, so assuming that you have this kind of diagram, then you can continue with X plus and so on. So in other words, on X plus, you will have another contraction, let's say with Z plus, and And then this might be divisorial, might be 5, but that might be another flip, and then you just repeat exactly the same kind of arguments. So you can complete this program. This process is called LMNP, and so you can complete this if you have all the steps. So it works if we have several things. We have all the necessary contractions. If you have all the flips, and finally, something which is not clear at all is why this thing will stop at the end. So the process term. In fact, this termination bit, even for complex scale, is still a very major open problem. So anyway, that's how it works. And so let me just mention some of the known code cases. So I will just mention characteristics. The positive for complex case, there are too many cases now. So here essentially we have dimension 2. Now, of course, you need to put some conditions on the singularity. Like, for example, you can have some nice conditions, and then in dimension 3 also. So at least when K is the closure of a finite field, and the P here needs to be more than 5 for some technical reasons. So in this case also everything works at least when X is smooth. And the B is just equal to 0, or otherwise you need to put some strong conditions here. So if in dimension 3, if K is more general, then there is something weaker than this, which is more difficult to state. So anyway, there are not so many cases known, especially in positive characteristics. So now, most of the talk will be about flips, because I have already discussed minimal models in previous lectures. I even constructed models for surfaces and for, like, in some cases, semi-scalable, maybe finite. Okay, so flips and finite generation. So the flip itself, as I discussed, there is a completely geometric thing, but you can in fact translate it into something very algebraic. So suppose that we have xp as usual, and suppose that xp is a flip contraction. Then I can define this object. Let R be. So one thing to remark is that to find the flip, to construct the flip, is a completely local problem, or Z. Find X plus is the local problem on Z. So in other words, you can write your Z as a union of maybe finitely many open sets, and then if over each of these open sets you find X plus, then you can glue them all together. The reason for that is because on the side of X plus we have an ampleness, and ampleness in a way is unique. So it doesn't, if you have locally, you can just glue them together. Anyway, so we could assume that and the Z is affine. This is just to make the notation easy after a natural adjustment. So for instance, let's say Z is just a spectrum, some ring A. Then I can define this algebraic object, define R to be the direction of 0 m times k plus b, where the m are all the non-negative integers. So this object has a natural ring structure. So this is a graded algebra. So you see that if you take the m to be equal to 0, then you have h0, the sections of 0. The sections of 0 are just exactly a. So this a is equal to the degree 0. So in degree 0 you just have a, but in higher degrees you might have more complicated stuff. So it has a natural graded structure, and it's also an algebra over this ring A. Okay, now why I define this kind of object is the following thing. So it's a well-known fact that the field exists if and only if the R is finitely generated. So finitely generated, you can think about, this could be like a polynomial ring, or it's just a quotient of a polynomial ring. So here you have something which is completely geometric, you translate it into something completely algebraic. And so the whole story of flip has to do somehow with the interaction of algebra and geometry. You need somehow to understand the relation between these two. So maybe I'll just explain a little bit. So if the flip exists, then in fact R is also the same as, and just write it as h0 n times kx plus. In other words, you can calculate this ring on the other side. And the reason for this is because you don't contract any divisor here, you don't contract any divisor there. And the sections here are just rational functions, and so they just transfer from here to there, essentially for free. So this is a trivial statement. There is nothing deep about it. And now we use the fact that this guy is ample over Z. So when you take the ring of some ample divisor, again for some elementary reason, it's going to be finitely generated. So this is finitely generated because this is ample. So ample over Z, but Z is affine, so ample is the same globally or relatively. So that's how you go from here to there. And the converse is actually it's also quite simple. So converse is if the R is finitely generated, then you just put x plus to be the approach of R. So if you don't know what is product, then you have a ring which is finitely generated in the quotient of polynomial. Then, so when you take the quotient, you have an ideal, and the ideal is generated by some elements. And roughly speaking, those will give you the equation that it explains. So these are all more or less classical birational geometry. This is well known already for a long time. Now let me give you one example of a flip. So this is quite explicit and very elementary. First we take Z to be the variety defined by xy minus zt inside A4. So the x, y, z, and t are just the variables, that's the coordinates. And then you define these objects that have to surface inside A4. You can easily see that it has only one singular point. Which is just the origin. So let me say the digit A. So it has one singular point, and the singularity is quite simple. It has multiplicity 2, so it's say the simplest kind of singularity. In fact, in lecture 4, I talked about this kind of object. It is just a cone over some surface. I will tell you that in a minute. Okay, so now we can blow up this singular point. Blow up the point A to get a smooth one. So you have a singularity with multiplicity 2. When you blow it up, the multiplicity will drop, and then multiplicity 1 is just smooth. So anyway, you can work it out whether it is explicitly by simple calculations. So you could either say that this is A4, this is, let's say, Z. You can blow up the point of A4 itself. Then you get something here, and then you get a copy of P3. This is the exceptional. You just replace the point with P3. That's what the blow up is essentially about. And then you take the Z here, you will take the transform of Z and you intersect it with this guy, then you will get 1. And the intersection here will be again a divisor contracted with a singular point. Z. Anyway, these are all elementary, you can find the Caucher. So to put it short, then Y to Z contracts only one divisor. And in fact, this divisor is just given by the same equations. But now this is inside P3. That's because you blow up the point on A4, the exceptional, what you get is P3, and then the equations on Z will just give you the equation of the exceptional divisor. Now, if you know a little algebraic geometry, you can recognize these objects. It's just a quadratic surface, and it's actually just P1 cross P1. So if you take the so-called Segre embedding into P3, it will give you exactly the same equation. So this is P1 cross P1, and then it has shape like this. So each component is factored, it will give you a familiar line, the familiar projective line P1, and then here what happens is that you can contract this divisor E not to a point, but you can contract it to a curve by contracting the curves in the family. So if you replace all these curves in this direction by points, you will get just one P1. I will put it in this way. We can contract in two different directions. Given by this family of curves. Now they're given by the two projections you want. So what you end up with is something like we have y already, we get x in one direction, you get x plus, and then you have the z, which is the original thing. So E is here. If you contract it to a point, you just recover the z. If you contract in one direction the family, you get x. If you contract the other family, you get x plus. And these are in fact just blow-ups in the usual sense. Okay, now this is more or less a flip. In fact, this is what we call a flop. A flop is something similar to a flip, but to make it into a flip, I need just a little bit adjustment. So we can take, let's say, b plus on x plus, so that it is ample. And then take phi, take b to be this birational transform, in other words, just this fullback. Then kx plus b is negative. For the set, but if you come to this side of the story, this one is positive over the set. Okay, there is only one little thing to note is that kx is in fact just trivial. Kx plus is also trivial. And this comes from the fact that the canonical divisor on Z is in fact Cartier. So it's a Cartier divisor, but when you take it together with divisor, it's not Cartier anymore. So this just comes from the fact that Z is a hypersurface inside A4. So it's a Goran's type variety, particularly this case, that's the Cartier divisor. So that's an example of a flip. That might actually be a simple example of a flip. So again, should emphasize that this has nothing to do with characteristics P. Just an example in any character, complex or whatever. So in characteristic 0, the existence of flip, this finite generation is in fact really the most difficult part of the whole story of minimal models. But in characteristic P, at the end of the day, it might happen that in fact the so-called base point freeness, the contraction theorem themselves might be the most difficult flips. But anyway, so the question is now how to construct flips, how to prove this finite generation. There is a very really fundamental idea of Shakurov. Say that we can reduce to a special kind of flip, and we call them PL flips. So if you are on a random kind of X and you have this flipping contraction, there doesn't seem to be any way to show that this ring is finitely generated. So by that I mean that there is no obvious way of doing induction, which is essentially how most of the theorems in birational geometry are proved. So, for example, you don't have any nice divisor to restrict to and maybe lift something from this divisor. There is just nothing maybe nice there. And the idea here is that to change this flip to something where you have some natural inductive candidate. Okay, suppose that xd is before and x to z flip contraction. So we like to find x plus, and here how one can do it. Suppose that there is a resolution. Well, there is a what we call lower resolution. So this means that you make everything essentially smooth. You have, let's say, y to x is equal to g. So this means that y is smooth, all the divisors become nice, smooth, simple, normal crossing, and so on. Of course, it does not exist always in characteristic P, but at least on 3 folds, this is already known, so you can assume that it's fine. But the characteristic series is always known in any dimension. Okay, suppose we have this object, and then now let B of y to be the tilde plus. So here the tilde is the birational transform of P. So in other words, for every component of B here, you just take the same component upstairs with the same coefficient. But the E here is a reduced exceptional device. So in other words, for every exceptional prime divisor, you just take one here with coefficient 1. So there is no multiplicity here, just irreducible. Okay, now assume that this pair is KLT, and this so-called KLT singularity. Then we can write a formula of this form. Ky plus Py is just the product of Ax plus P. But to make it right, you have to add some exceptional device. This F is effective, it is also exceptional. So this just comes from the chaos condition. So when you have chaotic singularity, they just tell you, just by definition. You could take, you could say almost this is the definition of chaos. Okay, we write this formula, and now we try to run a program not on K plus B originally, but we try to run a program on B. So we try to run a minimum model program on Ky plus B1. So what is the advantage of this? Well, I mean, it should be relatively overextended. So the advantage is that here, essentially many things can be translated into this divisor here, divisor F. So the point is that in every step, some little bit of thing here missing here. This is not enough. We actually need to put some more stuff there. So here I need to put become a bit more technical. What I will try to do is that Kx plus B here downstairs, because you are in a birational situation itself, is essentially a big divisor, so at least up to Q linear equivalence, you can write it as something effective. And then here we also need to add really the components of this MT. Maybe you can, for the moment, ignore these technicalities here, but what is important is that we run a minimal model program on this Py. So here F, and then you will have some other stuff. So let me get this right. So essentially here you have something that comes from M. we're not going through all this little stuff. So the important thing is that if you try to run a minimum order program and you divide it, then in every step, the contraction or the extremal rate or the curves involved, so to be more precise, the extremal rays, they intersect some component with coefficient equal to 1. So that's the whole story. We will write it in a way, in a form, by essentially artificially adding exceptional divisors, component of n, and so on, so that every exceptional divisor, every component of m here will appear with coefficient 1. And because of the way this formula is written, when this divisor intersect any curve negatively, then at least one of those, in fact, should contain that negative curve. So what is the advantage of this? Then we can do induction. So probably the best thing is if I just draw a picture. So suppose that we have a flipping of some situation, and then you have, let's say, one curve contracted to a point. And now in this program, there will be always some component, let's say S, which contains this curve. Now the advantage is that in this situation, if you try to construct a flip, then you have at least one natural quantity to be done. This is exactly S. Because the S has coefficient exactly 1 in the boundary, then you could, let's say, restrict to S, and then this is just Ks plus some boundary on S. Then we can do induction. There is this natural thing. But at the original situation where we have a flipping, the P does not have any component of that 4. So there is just no reasonable way of doing induction there. But here there always is a picture like this, and then you can do induction. Anyway, so the bottom line is that we will only need so-called PL flip. So I will not give a separate definition for this PL.
So do you mean intersect or include in some component?
Yeah, so it will intersect actually negatively.
Negative. Yes.
And so it will then have to be inside this component. So actually, I mean, that's not really the end of the story. You need to run this program. You show it terminate. Termination is again a completely inductive thing because you have always your flip inside some divisor, and then at the end you need a little bit of adjustment to arrive at the end. So here at the end so we precise after removing some divisors. So maybe this is not very precise, but this is the main idea that we want to always have this situation. So I can then make this definition here. Okay, suppose now we have a pair of these four. X, we have P, and then we have S. So just to make the notation a little for understanding, I will just take this S outside. So essentially S then is a component of the boundary coefficient 1. So I can just separate it. And if S is just something like in this picture. So then I assume that S is not a component of B. So we start with a pair like this, and then assume that now X with Z is a flipping contraction. For this pair X B plus. So in other words, let's say, for example, you have a threefold birational contraction, you contract maybe just one curve, and then K plus B plus S is negative on this curve. Now, to make this into a PL flip, I also require that S is also negative. So in other words, if you have any curve here contracted, S should intersect with negative. So in particular, S will contain all such curves. So everything will be decided S just exactly like in this picture. So if you have a situation like this, then we say that we have a PL flip. So I don't know why Shapiro called it PL flip. This goes to maybe 20 years ago. But actually it would be much nicer if you just call it an inductive flip. That's exactly what it is. You have some way of doing induction. Okay, so then you really only need to contract flip for this kind of flipping contraction because of this process that I have vaguely explained.
You have a PL flipping contraction.
Yeah, so in this case we have X to Z, and then we have a, sorry, we have a PL flipping contraction, and then for the whole thing, then we set it to a PL if it exists. But if we don't have it exist, we just say it's PL flipping contraction. So this was one of the major things, maybe the most important works of Shapiro are all related to this thing, and then he just put forward a strategy to show how to construct X plus by proving this finite generation using the component S. So I will try to say something about this in a few minutes, but let me just mention this main theorem of this lecture. So this is characteristic. Stuff here, characteristics more than 5 or something. It's not such a big deal, and then assume that XP is KLP of diameter 3, and then there are some others. So because not everything works perfect, there are always some annoying extra assumptions. So this is KLT, and then B has coefficients in this set. These are so-called standard coefficients. These are all for technical reasons, but at the end of the day, they should be removed. Then in this situation, then the PL flip exists. Let's put plus S just like in the picture. Then PL flip exists like fact that it implies that flips also exist as So because I have this component S here, so technically this is not KLT, this is what we call PLT. But you don't have to worry too much about that. It essentially looks like KLT except that you have one coefficient here, 1. So then one can construct flips for this kind of pair. And in particular now, if let's say X is small, K over the closure of a finite field, then when all the flips that we need exist, and in fact we can run a minimum with the program. So here the B is equal to 0. So in other words, of the finite field for just a smooth projective variety is threefold. You can run the minimum modular program just in the usual standard that I explained here, and then these will stop and then end up with a minimum model or more refined. So essentially all the components were known already except the flip, which will come from this. Finally, let me give you some ideas of how one proves the existence of PL flips. So most of this that I will say, in fact, it has nothing to do with characteristic P, it's working in any characteristic. And we will mention this goes back to Shakur. Suppose that a PL flipping char. For some pair B plus S, so we have the distinguished component with coefficient 1. And then K plus B plus S is negative over S over Z. So as usual, we could assume that Z is affine. And then we need to show finite generation to construct the flip. So we need to show that this ring, I'll write it again, S. So it's exactly as before, except that now we have this one component with coefficient 1. So just the notation is a little bit. So we need to show that this ring is finitely generated. So as I have been trying to explain, if there are no S, then there are no way of, at least no reasonable way of showing it finitely generated. But because we have this S here, there is an obvious natural inductive element here. So what we try to do essentially is to restrict this R to S and just see what happens. So because I want to restrict to S, we could assume that S is not a component of K plus B plus S. So if it happened to be a component, you don't need to change the K linearly. It just avoids S. So this is a trivial thing. And then when S is not a component of the divisor, then every element in this edge theory is just a rational function.
K is plus B.
Still, S is here, but the K, so the K could be something like D minus S. And then D minus S will remove that S. Because the K is not a unique T, it's not too linearly to it. You can always add the divisor of some rational function which will remove that. So this is a very elementary thing. It's just because of the K, you have some flexibility there. Okay, so when S is not a component here, then the elements here are just rational functions, homomorphic functions. Their poles don't include S, just by this condition. So because S is not a pole of such a rational function, you can just restrict there, it makes sense. So that's how to imagine this in terms of rational functions. Otherwise, you can just use abstract algebraic geometry, then we have...
So you don't need to use the K plus B.
Sorry, what is it?
I mean, if you just assuming K plus B to be the big, you need some multiple of K plus B.
Yeah, so because I have assumed that Z is already affine, so this divisor is in fact B. So if you take multiples, then you will have a lot of functions. This is not a problem. Okay, you might have to shrink that set, but probably it's not necessary. Anyway, this is really very elementary. Maybe you can look at so-called child lemma. You want to change
because you view K plus B as a pure divisor. So you take multiple, you can divide back to avoid S.
Yeah,
That's the question.
so the B itself does not contain S. And now, so you could change, you can take the divisor of some alpha and then add it to Kx plus S. And so that this will not contain S anymore. So the B anyway does not contain S. So you can find out some rational functions so that the divisor of the function class will not contain X. But this bit is still just a canonical divisor. Anyway, so Charles' lemma says that after linear equivalent, you can avoid any subrank. Because K is not Cartier here completely, but still Cartier outside the singularity point. So on the smooth local, you still have Cartier divisor. Anyway, so we have now a restriction map. So in other words, from R, I have a natural way of restricting to S, but here on S I have this guy. So anyway, if you are not so happy about this statement, this is just an abstract algebraic geometry statement. You always have the option of restricting sections to whatever you like. But I think imagining them in terms of rational functions is easy. So we have a natural restriction map of this form, and then this guy is now on S. Now, so this will factor, let's call the image of this. Or the image of this map. Denoted by R restricted to S. So what we restrict the R to 10. Now the interesting thing is if I claim that R is finitely generated if and only if the restriction is finitely generated. So this direction is clear. This is finitely generated. Restriction is always finitely generated. But the other way is less obvious. So again, it will involve some elementary changes here. So one thing I need to do first, the first thing to note is that since K plus B plus S and also S, they are both negative over Z, in other words, they intersect everything negatively. And here I need also to put it with technical thing, but you probably should not worry too much about it. And assuming that this is extreme of, so if you don't know what it is, just ignore it. Anyway, we can, by this, the fact that they are essentially proportional, then there will be, you can find two numbers A and B, natural numbers, such that M times, so A times Ks plus B plus S is linear to B times S. And of course, to have these kind of relations, I could just assume from the beginning that everything is rational. If it is not rational, you just need to change the coefficient a little bit to make it rational. So that's not a big assumption. So essentially, they say that both divisors are negative, so they are just proportional. Because they did not find, you can write it in 4. Now, some simple algebra tells you that R is finitely generated if and only if the ring of S is finitely generated. So when two divisors have this kind of proportional relation, then finite generation is the same for both of them. And as I said, it has just some simple algebraic reasons. So the point is that when we restricted the algebra to S, for K plus B plus S, maybe still this doesn't mean so much. But when we change to the ring of S, then it really means something very nice. So that would avoiding some technicalities, assume that, or just choose some divisor P linear to S. So assume that S is not a component. So again, because I want to interpret it in terms of rational function, and then it's easy to restrict it. So it's then obvious that the ring of S is finitely generated if and only if the ring of P is finitely generated. So these are the more or less trivial statements. And because they are linear, they have the same section, so finite generation is the same. But now we have this exact sequence. So I have the range given by this divisor P. And I can restrict it in the sense of the rational functions. I can restrict it to S. So this is just a restriction of this algebra. And if you don't like this kind of ideas, you could just ignore the T and say that you restrict the algebra of S. S just in an abstract algebra geometry sense. Okay, then the kernel of this is this object just direct sum of M times D. And then because we are restricted to S, you need to put minus S. But on the other hand, the S and D are linear. We could also replace this by D. This is isomorphic. 0 M minus 1 times D. And here is the key idea. So this object is more or less the same as this object here. The main difference is that the degrees are shifted. And that's exactly what we need to prove the claim. So essentially, if this guy is finitely generated, it will give you finite generation of this because you can just drop degrees and do induction using this curve. Then, so if you take, let's say, alpha in some homogeneous piece here, then we can write it the polynomial in finitely many fixed elements. So this is essentially, these elements are essentially the thing will give you the generator of the restriction. So this is not 100% correct. You still need something from upstairs, but it's almost saying that you just take generators of elements giving generators of the restriction. So let's say you take alpha of a certain fixed degree, you take it down here, it's written as a linear combination of the polynomial in a certain finite fixed element, but that you can also consider the polynomial here, you don't need to go down. Then, when you write it, then the difference will be given as an element here. But that element will have you have a drop of the degree. You will have something of smaller degree. So you replace alpha with something which has degree more or less. And then you repeat exactly the same with a new element. So all you will need is the finitely many elements here which will give you a generator, but maybe here you need also just one element put together, and then it will give you a set of generators. Okay, that's anyway, these are quite simple and elementary. So this guy is finitely generated. Of course, here we are talking about the algebra of D, but this is the same as it's the equivalent to finite generation of R restricted to S. So these are all actually very elementary, but I won't go too much into the details. So anyway, the claim then reduces the finite generation to proving finite generation of the restriction. Now, if you are very lucky, so I'm not this lucky, but maybe you are. If you are very lucky, then the restriction of R to S, maybe this is just equal to the section given by divisor. So here there is a subtle difference. Here I restrict the divisor first, I take the section of that. But here there is a completely different thing. Here I take the section first, then I restrict the rest. So these are not the same objects. Because you always have inclusion here, natural. So as I said, if you are very lucky, you might have this equality. If you have this equality, then by induction, this guy is finitely general. And therefore, is finitely general. But in most cases, this does not happen. This is not equal to that. This will be just a strict subset. And then the challenge is to find something, maybe not exactly this, but something related to that. So, in the general case, we try to find maybe not S itself, but some birational model, maybe a resolution, some birational model of S, and also find a divisor and a boundary bt on T such that if you restrict your R, you can also restrict it to T because these are elements of the rational function, so you can restrict. So of course the T itself is not on X, it's on some birational model, but the restriction to T is exactly the same way. And this restriction now is given by the sections of M times AT plus T plus BT. So these are really the major contributions of Shapiro. You realize that you don't have this equality usually. But if you go on some appropriate birational model, you will hopefully be able to find some divisor, some boundary, so that the algebra restricted to this T is given exactly by this section of the divisor. But even though this is not on S, but this is still has dimension at least one less, and therefore you can apply induction. So in characteristic 0, finding this T has to do with, anyway, in any characteristic, it has to do with lifting section. So the problem is to identify what the restriction of R is the same as identifying those sections which lift to the ambient space. So in characteristic 0, one uses a vanishing theorem. So to identify so you go on S or any birational model, you just ask the question, which sections actually come from the ambient space? So these are usually given by vanishing theorem. So here, to make more precise, you have either vanishing or Kawamata feedback. Nasal. These are all essentially the same category, and then, of course, the applying this vanishing theorem is not straightforward. That also involves a lot of technicalities, but so the techniques actually came mainly from analysis, from people like Keel. Okay, so then you ask the question, what to do if I see P? There is no such vanishing, but then fortunately there are something Not as good as in this zero case, but still enough for this triple kind of situation. So this is the so-called S0 sections. So I will then try to explain a little bit this techniques. So as far as I know, this belongs to Carl Schwitt. So we take a pair, let me also just change the notation, x delta, and characteristic 3. And then remember that we have a Frobenius map and a trace map and so on. Here let's also assume that p minus e to the e minus 1 times delta t. So there is such as if and only if p does not divide the index. But for this flipping situation, this is not really a problem because there is always some ample divisor, there is a flexibility to change things, so you don't worry about it. You can find some E that you have this guy being a counting device. And then remember that we have a trace map. So I'm now getting over 75. Is that okay? Maybe because the final lecture, then I'll finish it and have a rest. Okay, so we have a trace map of this form. This is just given by duality. This goes to OS. Now, let's also fix a Caucher device. Then we can tensor M with this trace map. This is just the trace map. I already wrote, so we can tensor this, then we get FE lower star. Actually, I would take n times. Not only E, if you take any natural number, you have the trace map, so this particular n. Then I take n times E for being pushed down to S. Divide the same divisor, and then I tensor with M, then I get here e to the E times n. Then it goes to and so this is again a kind of trace map, and then I will apply HC. So let's, just for simplicity, let's call this L. So I have from H0, maybe I call it N. So I have from this shape L and E, I have a map X0 or X. Then the idea is to, instead of looking at all the sections of this divisor, you just look at the sections which come from E. Because these are the kind of sections that you can control. The rest, maybe just have no control over them. Let's just put a name for this. Probably this phi and E. Then the idea is to define the S0 sections. There is yet some notation for some good reason, but you can probably just ignore it. This is just a notation. So S0 of sigma M is the intersection of the images of all other words, this is an asymptotic kind of construction. One n may not be enough. You need to look at all the possible n's. And the reason is for that is so usually you might have some positivity here, and it becomes larger and larger when the n becomes large. So you have more control. And the sigma here is, actually this is some kind of ideal shift, but this is similar to the complex geometry case when you have a line bundle and then you just multiply with the multiplier ideal shift or something. So in that case, of course, the sections are not equal to all the sections of M. It depends on how small the ideal is. So in roughly speaking, this is also what it's really doing. Say that the world the singularity is maybe the less section you will have here. This ideal will be smaller and smaller. Okay, so this is just a definition, and now the important thing about this kind of section is that if the M can be written as n plus delta plus something ample, and for instance, let's say if T is a component of delta with coefficient 1, so this is like saying that this is more or less like a logarithmical sense. There is a more general thing. Let's say if T is any so-called FP or center, but for simplicity, let's just take one component with coefficient 1. Then the statement is that there is a natural surjective map from this S0 section of M. So here to make it look better, let's put it with the delta here. It's the sigma for the delta and also x. Let's put the delta. And here you have some restriction to your center, and you will have some delta that's going delta C. I'm sorry, this is for the moment of delta, and then you have a restriction onto section. So in other words, you go on T, you have your divisor restricted there, you will get some, you apply the freeness and so on, you decide that you get some multiplier ideal over there, and then all the sections of M plus tensor we did ideal in this notation, then they will all come from the ambient space. So not all sections will be lifted, but at least some will be lifted. And in particular, if you have a strong positivity property for M restricted to T, you can in fact identify this with something more familiar. Maybe put it at H0 or something. So that's the basic idea. Instead of vanishing theorem, you will find this kind of technique. Okay, I will start.
Any questions?
In characteristic 0, you have to work on, you start with S, but you have to change the model to T, right? And in this case, you don't have to change the model to T.
But here also you will have, this is not all the story. You need to take infinitely many model given on X orbits. Infinitely many resolution, you will get the sequence of divisors and so on. But then by some ideas of Shapiro view, essentially when you go on S, or here T, then all these divisors somehow come from one single model. So you can somehow replace that with just one model. And that comes from the induction, but you already know a lot of things downstairs. But on the level of X, yeah, that's kind of difficult to get one model.
And how about determination?
So determination so far, in the case that I stated in the theorem where X was smooth, so the dimension is 3, the P is equal to 0, or if not equal to 0, you put a very strong condition on that. Then determination is identical to Shapurov theorem. There is nothing new. But more general termination is don't know. So determination is also a major problem.
So why the coefficient has to be standard coefficient?
That has to do with some technicalities. When you restrict to this S or T and so on, in characteristic 0, so let's say you get something like this. You restrict to T, then you have KT plus delta T and so on. And this lemma has a natural final structure. That's come from the definition essentially. But in characteristic case, final is not good enough. Instead of final, there is a notion called global irregular, or in this case, it will be relatively irregular. And that is extremely more stronger than just a final. And these people need the standard coefficient just essentially to control that. When you have that kind of coefficient, then again, there is another theory of Shapurov called complement. You can try to use that kind of thing to show that you don't have that final, but in fact you have something like globally regular. So if you have a random wild kind of coefficient, then we just don't know. Even on P1, it's not easy to see when you have global regularities.
Any other questions? Okay, so if not, then I would like to take this opportunity to thank Professor Birkar again for preparing these wonderful lectures, these efforts. Thank you very much.
I should also thank Chungkai for organizing these things, and then thank also all of you for coming to listen to the stuff. And so I'm kind of a beginner still in this direction. I'm giving up enough. So I tried my best.
So we are looking forward to see you next year.